Thanks all for waiting. Yep, so we're going to be talking today about some devices that we've been developing for dust mitigation application on the lunar surface. And in particular, using this device that was developed through the this material that was developed through the REVEAL survey collaboration called chemically modified reduced graphene oxide. So just to highlight the overview of the talk is that we were able to produce these electro-dynamic dust shield systems, these EDS systems, using a conductive nanocomposite material. We produced both two-phase and three-phase EDS devices, and we found that they were efficiently able to remove the deposited dust. And in particular, what was kind of cool was we saw that when we introduced UV light to the system, the voltages required to remove the dust actually decreased significantly for these two-phase devices. And finally, using a dielectric cap on top of our bare devices eliminated any electrical discharge while still maintaining the ability of these devices to clean dust from the surfaces. So the basics of EDS are shown here, where you can have either two-phase or three-phase devices. The two-phase is shown on the right-hand side in the B column. Three-phase is shown in the A column. And the differences are that in the two-phase design configuration, you generate a standing wave potential above the surface, while for the three-phase, it's traveling wave. The device sizes that we used are shown on the bottom here, and we're ultimately limited by our ability to manufacture these devices. That was kind of a just limited by the ability to make and press them. So this is what the fabrication process looks like. Is we start with the in A, the functionalized RGO, which is then spray coated onto the polymer substrate. In this case, we are using HDPE. But it's important to note that the polymer substrate can be changed to a number of different materials. That they've done it with polysulfones, such as Kapton, HDPE, etc. So it's a generalized process. After the spray coating application, heat and pressure are applied to infiltrate the spray deposited material into the polymer substrate. This is what it looks like here. We have a stainless steel mask. We spray that mask with the chemical, the RGO, resulting in the pattern substrates that you see here. We tested two different device configurations for this work, a rough condition and a smooth condition. And the difference between those is just the heat and pressure applied. The EDS system looked like this. It was a high vacuum chamber. So we ran all of these experiments at less than 1 × 10⁻⁶ torr. We would deposit the dust through a screen using LHS1 here. So we could evenly coat the surfaces of our devices. We did that deposition in atmosphere, then close the chamber, pump it down, and run the EDS. The UV lamp was mounted above and just to the side of the devices. And these are the images here on the right show the devices before dust deposition. And we're using black HDPE in these experiments just because it creates a high contrast with the dust. And so in C, you can see the devices with the dust removed. And this is what that looks like. I think this should play. Yep, and so running the EDS device, you see that the dust flies off of the surface, and we see that it happens rather rapidly. Showing here the rough devices in the red, the smooth devices in the blue. Those rough devices rapidly clean the dust from the surface. Within the first 20 seconds, you're removing almost 90% up to the maximum cleanliness. The smooth devices did not reach quite as high of a cleanliness, but one important thing to note here is that with multiple tests, we would run each of these devices 5 or 6 times. We did see a slow degradation in their total cleanliness. And I'll talk about that a little bit more in a minute. And so this is just an image of what the devices look like freshly deposited after 10 seconds and after 120 seconds. You can see that most of that cleaning is happening sort of early on. For the devices where we ran with the illumination in UV, you really see the effects of that degradation in subsequent tests. Showing here for the rough devices, the first test, second test, third test, and fourth test, that total cleanliness starts to decrease and the onset of cleaning can sort of be delayed as well. For the smooth devices, we see an even more rapid degradation in that cleaning ability. This is what the materials look like using an SEM before, after use with no V, and after use with UV. And we see that RGO material here, the boxes are zoomed in down below, is initially sort of flaky looking. After use, we see that some small submicron particles become embedded in that CMrGO material. Those we cannot remove. They get fully embedded into the materials. And after UV, you see even more degradation of those surfaces. We also tested the three-phase devices here. Oop, I'm not sure if I can play that. Well, this is what the three-phase devices look like before turning on the devices, after the deposition, after 40 seconds and after 300 seconds. And what was interesting with these devices is we saw that it was actually a function of pressure on what the ultimate cleanliness that we could reach was. For devices that we allowed to pump down in the chamber overnight, reaching pressures of less than 10 to the -7 torr, we actually got better cleanliness than the devices where we ran the tests after only a couple hours of pumping. And the reason that we think about that happens is because in the lower pressure tests, you have more water adsorbed onto the surfaces of the grains. That increases the grain cohesion. After pumping for 24 hours in that high vacuum environment, more of that water is desorbed from the surfaces, decreasing that intergrain cohesion. Finally, looking at a couple of capped devices. The capped devices we found also were able to achieve good cleanliness. It's not quite as good as the uncapped devices, although they did require slightly higher voltages applied to the traces in order to get that dust removed. What was nice, though, is that these devices did not degrade over time. And so we showed that putting a dielectric cap on top of the EDS devices effectively eliminated the degradation in the devices over time, eliminated any micro discharges that we see upon application of the EDS. Finally, I just wanted to talk about, and I'm not sure if this one's going to play either. Ah, good, it does. Some recent experiments that we're doing. Now I have instituted the ability to deposit dust under high vacuum conditions and run those EDS devices multiple times without ever exposing the system to vacuum. And so what I'm showing here, if we go back, is initially I am depositing the dust using a shaker above the device. Then I turn on the EDS while still maintaining that shaker going. I turn off the EDS, deposit more dust, and turn on the EDS again. And so we can do these tests that are more akin to what we would find on the lunar surface, where the dust deposition is actually happening in vacuum. So moving forward, we're going to continue testing some of these devices by dropping the charged dust grains onto both the activated surfaces, and we're going to be looking at EDS devices in flexure. So what I've shown here is flat devices, but the nice thing about depositing this material onto thermoplastics is that they're flexible, and the thermoplastic polymer, the CMrGO polymer, will maintain its conductivity despite multiple flexures of this material. And so it's very good for flexible devices, and we're going to explore that a little bit more. We're also exploring some capping materials such as nanostructured coatings that may help us to better eliminate the smallest dust grains that were difficult to remove with the current configurations. And finally, we're going to look at incorporating additional mitigation strategies such as vibrational tribocharging or electron bombardment that may further increase the efficiency of these devices. So with that, I'm happy to take any questions.
Okay, we have time for questions.
Hey, Micah, Carl Hovis, APL. Really interesting work you guys are doing. So in application, would this have to be done under vacuum then? Would astronauts have to use this to clean the spacesuits outside, or can they do it in the crew capsule under atmosphere?
So EDS, when you run it under lower or higher pressures and more akin to the atmospheric pressures, you do increase the risk of breakdown and discharge. But it's not required. And there's been plenty of EDS tests done in the past that are able to, if you have a dielectric cap on these materials, still remove the dust at atmospheric pressure. And actually, being implemented for solar panels here on Earth for a mechanism of cleaning dust off. So it absolutely can run under atmospheric pressure as well, but you do need to cap it so that you're not creating those dielectric discharges.
Thank you.
Mhm.